So in the last video, I introduced this multivariable chain rule, and here I want to explain a loose intuition for why it's true, why you would expect something like this to happen. So the way you think about an expression like this, you have this multivariable function, f of xy, and you're plugging things in, but just that function itself, you'll be thinking of taking a two-dimensional space, here's our xy plane, and then mapping it to just a real number line, and I'll think of this as f as the output. So somehow our whole function, our function takes things from this two-dimensional space and plugs it onto this output. T you're thinking of as just another number line up here, so t, and then you've got two separate functions here, x of t and y of t, x of t and y of t, each of which take that same value for a specific input. It's not that they're acting on different inputs, x of some other input t and y of some other input. It's the same one, and then they move that somewhere to this output space, which itself gets moved over. And in this way, you're thinking of it as just a single variable function that goes from t and ultimately outputs f. It's just that there's multidimensional stuff happening in between. And now if we start thinking about the derivative of it, what does that mean? What does that mean for the conception of the picture that we have going on here? Well, that bottom part, that dt, you're thinking of as a tiny change to t, right? So you're thinking of it as kind of a nudge. I'll draw it as a sizable line here for like moving from some original input over, but you might in principle think of it as a very, very tiny nudge in t. And over here you'd say, well, that's going to move your intermediary output in the xy plane to, maybe it'll move it in some amount. Again, imagine this is a very small nudge. I'm going to give it some size here just so I can write into it. And then whatever that nudge in the output space, right, it's a nudge in some direction, that's going to correspond to some change in f, some change based on the differential properties of the multivariable function itself. And if we think about this change, you might break it into components and say, this shift here has some kind of dx, some kind of shift in the x direction, and some kind of dy, some shift in the y direction. But you can actually reason about what these should be, because it's not just an arbitrary change in x or an arbitrary change in y, it's the one that was caused by dt. So if I go over here, I might say that dx is caused by that dt, and the whole meaning of the derivative, the whole meaning of the single variable derivative, would be that when we take dx dt, this is the factor that tells us, a tiny nudge in t, how much does that change the x component? And if you want, you could think of this as kind of canceling out the dt's, and you're just left with x. But really, you're saying there's a tiny nudge in t, and that results in a change in x, and this derivative is what tells you the ratio between those sizes. And similarly, that change in y here, that change in y, is going to be somehow proportional to the change in t, and that proportion is given by the derivative of y with respect to t. That's the whole point of the derivative. Oh, no, with respect to t. And again, you could kind of think of it as if you're canceling out the t's, and this is why the fractional writing, this Leibniz notation, is actually pretty helpful. People will say, oh, mathematicians would shake their heads at the idea of treating these like fractions, but not only is it a useful thing to do because it is a helpful mnemonic, it's reflective of what you're going to do when you make a very formal argument. And I think I'll do that in one of the following videos. I'll describe this in a much more formal way that's a little bit more airtight than the kind of hand-waving, nudging around. But the intuition you get from just writing this as a fraction is basically the scaffolding for that formal argument. So it's a fine thing to do. I don't think mathematicians are shaking their head every time that a student or a teacher does this. But anyway, so this is kind of what gives you what that dx is, what that dy is. And then over here, if you're saying, how much does that change the ultimate output of the f? You could say, well, your nudge of size dx over here, you're wondering how much that changes the output of f. That's the meaning of the partial derivative, right? If we say we have the partial derivative with respect to x, what that means is that if you take a tiny nudge of size x, this is giving you the ratio between that and the ultimate, change to the output that you want. You could kind of think of it like this partial x is canceling out with that dx if you wanted, or you could just say, this is a tiny nudge in x, this is going to result in some change in f, I'm not sure what, but the meaning of the derivative is the ratio between those two. And that's what lets you figure it out. And similarly, that's just, you might call this the change in f caused by x, like due to x. Due to, I should say, dx. But that's not the only thing changing the value of f, right? That's not the only change happening in the input space. You also have another change in f, and this one I might say is due to dy, due to that tiny shift in y. And what that's going to be, we know it's going to be proportional to that tiny shift in y. And the proportionality constant, this is the meaning of the partial derivative. That when you nudge y in some way, it results in some kind of nudge in f, and the ratio between those two is what the derivative gives. So ultimately, if you put this all together, what you'd say is there's two different things causing an ultimate change to f. So if you put these together, and you want to know what the total change in f is, so I might go over here and say the total change in f, one of them is caused by partial f, partial x, and I can multiply it by dx here, but really, we know that dx, the change there, was in turn caused by dt. So that, in turn, is caused by the change in the x component that was due to dt. That was, of course, of size dt. And then for similar reasons, the other way that this changes in the y direction is a partial of f with respect to y. But what caused that initial shift in y? You'd say, well, that was, a shift in y that was due to t, and that size is dy dt times dt, you could think of it. So slight nudge in t causes a change in y, that change in y causes a change in f. And when you add those two together, that's everything that's going on, that's everything that influences the ultimate change in f. So then if you take this whole expression and you divide everything out by dt, so I kind of erase it from this side and put it over here, dt, this is your multivariable chain rule. And of course, I've just written the same thing again, but hopefully this gives a little bit of an intuition for how you're composing different nudges and why you want to think about it that way. Of course, you can see this and you see that the partial f kind of cancels out with that dx, and this partial y kind of cancels out with that dy, and you're left with the two different things that constitute a change in x. This one is only partially the change in f. This is also only partially the change in f. But together, they give the ultimate change in f. And I think that gives a very strong reason, if you break it down like that, why this should be true.